My name is LaurynHinckley. I am majoring in neuroscience and a student under my faculty mentor, Dr. Wiley. I'm studying the advances of tridecine alginate bioplastics as a delivery system of acetaminophen and ibuprofen. Acetaminophen and ibuprofen are over-the-counter medications used to treat pain, fever, and inflammation. The drugs were chosen because they are readily available. Many are familiar with the drugs as 25 billion doses of acetaminophen and 30 billion doses of ibuprofen are consumed per year. Current drug delivery systems include tablets and capsules, but is there an alternative to current drug delivery systems? Yes, I was first introduced to the bioplastics in the Wiley General Chemistry Lab, which were used to study the release of blue food coloring. The bioplastics contain tridecine and alginate, which make the bioplastics biocompatible, biodegradable, non-toxic, and inexpensive compared to current drug delivery systems. In the lab, bioplastics are made into films as shown in the front petri dish. Tridecine and alginate are two polysaccharides that form the bioplastics synthesized in our laboratory. Tridecine, as shown in figure 4, is derived from chitin, which is extracted from the exoskeleton of crustaceans. Films made of tridecine are flexible and incredibly water-soluble, which would have limited uses in an aqueous environment. Alginate, as seen in figure 5, is extracted from brown seaweed, which forms films that are very brittle. Neither polymer alone creates a workable material. In combining both polymers, as seen in figure 6, cross-linkages, which are the interactions between separate polymer strands, take form of hydrogen bonds or calcium bridges between the saccharides to create a bioplastic that is strong yet flexible. Thus, we can create a bioplastic that takes on the best characteristics of both materials. Cross-linking also creates a matrix in which organic molecules can become trapped and may be released into a solution at a later time. It is this use of the bioplastic for acetaminophen and ibuprofen that I have been studying. So how do we get the drugs into the bioplastics? First, a master mix is created with a 1-to-1 ratio of tridecine to alginate and water. This was then divided into 4 separate beakers, which would later become a control, which has no drugs, one impregnated with ibuprofen, another with acetaminophen, and one with both drugs. Lactic acid was added to these, which starts a hydrogen bond network. The beakers were then poured and separated between 4 petri dishes and topped with calcium chloride solution for 1 hour. The petri dishes were left in the hood to dry. After the bioplastics were dry, they were harvested and stored. The bioplastics were then cut into strips for release studies over a select period of time. UV-vis spectroscopy is a quantitative technique to measure the amount of a particular substance at a particular wavelength. This is done by measuring the amount of light photons that are absorbed through a sample of interest compared to a control, RO water. We determined that ibuprofen has an optimal absorbance at 220 nanometers and acetaminophen is at 250 nanometers. Due to the possible overlap from the wavelengths and contaminants, we moved from the UV-vis spectroscopy to use a high-performance liquid chromatography, or HPLC. The HPLC is a technique that separates components of a mixture using a combination of mobile phase and stationary phase. The mixture components are separated on a column that elute at different times, then are quantified by a UV-vis detector. A method was created to elute acetaminophen and ibuprofen at different times by changing the polarity of the mobile phase. An original method that was created slowly shifted the mobile phase from a more polar phase to a more progressively nonpolar phase over 25 minutes. The method was then improved multiple times to decrease the time to use less mobile phase. To determine the efficacy of these methods for analysis, calibration plots of acetaminophen and ibuprofen were prepared for the samples between 5 parts per million and 100 parts per million. These shown, as seen in figures 15 and 16, a high degree of linearity between the peak area and concentration. Now, we have a reliable method for quantifying ibuprofen and acetaminophen. I originally came up with standard conditions to base all of my trials on. The way our experiments work is that strips of the bioplastic are cut, masked, and immersed into a solution. Samples of the solution are taken and run in an HPLC. The standard mass of the test strip is 0.007 grams, submerged into RO water with a volume of 4 milliliters for 45 minutes. Also, the mass of the analgesic put into 4 plates is 0.3 grams. I then halved and doubled the standard mass, used various hydrochloric acid solutions, tested 2, 3, 4, 5, and 10 milliliter volumes and ran release samples from 2 minutes to 3 weeks, or infinite time. I then impregnated 4 bioplastic plates with half and double the amount of standard analgesics. So the question is, do the drugs come out? The answer is yes. I found out that there's an initial fast release, then the release rate slows over time, with acetaminophen and ibuprofen in figures 18 and 19. As you can see, ibuprofen is released from the bioplastic more readily than acetaminophen. We also looked at a bioplastic impregnated with both drugs. The most interesting finding is that between figure 18 and 20, the release of acetaminophen is comparable. Meanwhile, the release of ibuprofen increases between figures 19 and 20. However, there are some limitations with ibuprofen. Acetaminophen comes off at the column at 2 minutes, and ibuprofen comes off at 10 minutes. So ibuprofen uses significantly more methanol than acetaminophen. Then acetaminophen is absorbed at 250 nanometers, whereas ibuprofen is absorbed at 220 nanometers, which is the same wavelength at which methanol is absorbed. The net result is that methanol signal makes this difficult to extract the ibuprofen data for these runs. This does not mean that ibuprofen is impossible. We just have shifted to focus on acetaminophen. This will also allow us to do much quicker runs, use less materials, and get more results. I looked at varying the masses of sample, volume solution, the pH of solutions, and time as highlighted in figure 22. I also conducted trials on the effects of surface area, percent swelling, and reversibility for the rest of the school year. Here are my 12 data points that demonstrate how acetaminophen releases from the bioplastics over 5 academic semesters, showing a high level of reproducibility. I looked at the release from my standard mass of 0.007 grams and 0.014 grams, which demonstrates that doubling the mass doubles the release of pharmaceuticals, which makes sense. After realizing that the amount of acetaminophen released varies directly with the size of the bioplastic, I then went on to study if surface area affects the release rate. I conducted 5 trials with control samples of 0.007 grams in a strip and 5 samples of 7 milligrams of finely powdered bioplastics. I then made bioplastic powder by grinding up the bioplastic strips with a pestle and mortar. I then subjected the samples to 4 milliliters of water over 45 minutes. As you can see in table 1, the powdered samples show that acetaminophen releases more readily as the surface area of the bioplastic increases. After the surface area was tested, I then studied if volume impacts the release rate. Each bioplastic was cut to 7 milligrams and placed in various amounts of water over a 45-minute interval as depicted in figure 25. The peak area was then measured by the HPLC and shown in figure 26. Here it seems as though volume has an effect on the release rate of acetaminophen. The peak area, as seen on the previous slide, was then calculated to concentration of release and total drug release in milligrams as seen in table 2. The volume of the various samples over the release in milligrams was graphed as seen in figure 27. Overall, this shows that the volume of water versus the release rate is fairly consistent, which is why I chose to use 4 milliliters as my standard volume of solution. After I conducted my studies on volume, I was then interested in changing the pH of the solution while keeping the volume the same. Here, we collected data at 30 minutes and 45 minutes at 2 different pHs. RO water, as shown in pink, the pH of 7, and 0.15 molar hydrochloric acid, as shown in blue, the latter of which is approximately equivalent to stomach acid. At each pH, 2 samples were collected at each time and analyzed in figure 28. These data show that acetaminophen released more readily in a lower pH. This data was highly reproducible. In order to better understand the efficacy of these materials as drug delivery systems, I thought it was important to understand how much of the drug I originally put into the homogeneous mixture, as seen in figure 29, does not get included into the matrix of the bioplastic. I ran the HPLC for the parts per million of acetaminophen lost in figure 29 to determine the physical loss of bioplastic material after pouring the mixture into Petri dishes in figure 30. After that, I poured calcium chloride on for 1 hour and the calcium chloride was collected. These losses were made up to standard volume and acetaminophen concentration was determined by the HPLC. Table 3 shows the standard volume that the losses were collected in along with the peak area that was determined by BHPLC. The major loss in analgesic was after the calcium chloride was poured off. The loss in milligrams was calculated from this data, and the percent incorporation of the pharmaceutical was determined to be approximately 90%. So most of the drug that was originally added to the bioplastic homogeneous solution was incorporated into the bioplastic matrix. In order to better understand the real-world implications of drug delivery via bioplastics, the percent swelling was tested. A bioplastic that is immersed into a solution swells, as shown in figure 33. This is applicable because if someone did use a bioplastic as a drug delivery system, it would swell upon entering the body. Some factors that were explored that could impact the swelling of the bioplastic are the pH of the solution and presence of analgesics. To determine the percent swelling of the bioplastics over time, by taking the final mass minus the initial mass divided by the initial mass times 100. These measurements were taken over 3 weeks. In the 3-week trial, I left large bioplastic samples with and without acetaminophen in RO water, 0.075 molar, 0.15 molar, and 0.3 molar hydrochloric acid as seen in figure 34. When looking at figure 35, the RO water had the greatest swelling change, and the percent swelling decreases as the acid increases in molarity, which was expected. The percent swelling of the bioplastic without acetaminophen tends to be greater than the bioplastics with acetaminophen. This could be due to having a higher percent composition of chitosan and alginate. In figure 35, I showed the 3-week data as the difference between week 1 and week 3 is only 6% different. Due to the nature of the bioplastic matrix, I knew that molecules could enter the bioplastic such as water. So I was interested in studying if the bioplastic could be a potential uptake system. In this experiment depicted by figure 36, I submerged 7 milligrams of drug-free bioplastic samples in 4 milliliters of 100 parts per million and 50 parts per million standard solutions. I then left the samples to run for 2 weeks, compared the samples to standard solutions. The bioplastic absorbed a marginal amount of acetaminophen. Right now, we are not sure why acetaminophen does not go back into the bioplastic, but it could be due to polarity. The bioplastics could serve as a potential drug delivery system per acetaminophen and ibuprofen release data. The control bioplastics do not serve as an uptake system for analgesics, and the drug release is consistent with drug loading. Overall, for the acetaminophen data, 50% of acetaminophen is released after 45 minutes. Over 90% of the pharmaceuticals added to the homogeneous bioplastic mixture are incorporated. Also, the lower pH is from acid. The higher the release as seen in my acid trials. So some future directions, I would really love to revisit ibuprofen and optimize my method for obtaining ibuprofen data. Load other analgesics into the bioplastics to understand the release rate. And lastly, the long-term goal of the Wiley lab is to correlate the structure, size, and polarity of an analgesic with the release rate. Thank you to Sigma Zeta for funding this work under a 2019 research grant. Thank you to Lexi Warden Kelly Noah for their previous research, the Concordia Chemistry Department for the Space Analytical Instruments for donating the HPLC to the Wiley Teaching and Research Lab, and Dr. Wiley for your time and energy and support to foster interest in research.